have almost all the things at demo. Like you can come and visit and test our instrument before you make any purchase. Okay, which is not of the topic for you now. So you want to learn actually what is single crystal. How many of you know what is the purpose of IHBT by this machine? How many of you know? Or what it can give? Anybody know? Okay, so the purpose of this diffractometer, what IHBT has got, is to determine the structure. So you have brought the NMR, right? Last year, I think. NMR will tell you what compounds it is formed, like how many carbons are there, how many nitrogens are there, how many oxygens, there are single bond, double bond. So those things it can tell, but it cannot give you the structures like this, right? So the idea is you want to determine the structure like this, and the single crystal diffractometer, what you have got here, is the main purpose of determining these kind of structures. Okay, so that is the sole purpose of buying this machine. So whatever, but as the name itself suggests, it is a single crystal X-ray diffractometer. It is an X-ray diffractometer. Okay, so X-ray is the radiation what we use for the diffraction. Okay, I'll come to that why X-ray is being used. The simple reason for X-ray, why not UV or why not IR, why not radio waves? X-ray is because, so you are talking about your chemical compounds, right? Which may be plant extract or which may be some organic synthesis molecule. So they are all formed by carbon, nitrogen, oxygen, hydrogens. So what are the bond distance between them? So it is like carbon-carbon single bond is around 1.54 angstrom. Carbon-oxygen double bond is around 1.2. So we are talking in angstrom. So that means we need a radiation which is suited for this distance. So which is X-ray. X-ray is in the wavelength similar to the interatomic distance. So that is why X-ray is used for studying the diffraction experiment. So this is an X-ray diffractometer. But there is one additional information like single crystal. So single crystal is the sample which you are going to analyze. In an X-ray diffractometer, you can put anything to get the diffraction. Okay, so that is your polycrystalline material, or your thin films, your powders, your rubbers, polymers, whatever you can put, and you will get the diffraction. Okay, but that is an average diffraction. You will get the intensity versus 2 theta. What is there? How much is there? But you will not get able to establish the structures like this. Okay, so this is the structure of a sugar. Okay, sugar what you take daily in your kitchen. So you can bring and we can put it on the diffractometer and we can get this structure in few minutes. Okay, so that is the sole purpose of this instrument. So to get the three-dimensional structure, and this is the direct method and the most unambiguous method, means undisputed method for the structure determination, provided you need to have a sample which is single crystal. So that is why it's called single crystal X-ray diffractometer. Okay, so the idea is you want to see the molecule like this. In simple words, this is just, I don't want to get into lots of basic things, but still, like this is a sugar sample. So you can take under the microscope and zoom it in. So can you able to see the structure like that? No, because you have some limitation. You can go up to nanometers in your electron microscope, right? You can really go to the nanometer range and then you can see. But you cannot see in angstrom, which is much, much smaller. So that means you need to depend on some other techniques. So what are the other techniques? Here I say, these are the different analytic techniques you use in your day-to-day laboratories. So you use an NMR, you use an AFM, you use a CM, you need an XRF, you use a mass spectrometry, you need some elemental analysis. You do all these things, but none of them will be able to provide you the three-dimensional structure. The limitation is the magnification or the resolution, and these are all only fingerprinting techniques. Like it can tell, but it will not be able to give you the structures. Okay, so then what is stopping you from doing so is, or what is the alternative you can do is, you can study about your 10th class or maybe 12th class diffraction experiment. So if you shine your light on any material, it gives a diffraction. So from those diffraction, you can get the information about that particular material. So that's the same thing what we use here in X-ray diffraction, provided what we use here is the X-ray is the radiation for the diffraction experiment what we use. So we know that when we shine an X-ray on your crystal, so crystal, what is crystal then? Okay, so it has contained a periodic repetitive atomic units. That means, okay, so the difference between a regular polycrystalline sample or a single crystal, what is the difference is, in a polycrystalline material, you don't have a long range order. Okay, so there is no periodicity which is till infinity. So it lasts after some time. It has a short range order. But in case of single crystal, when we discuss, so single crystal has a periodicity. So when you shine your experiment X-ray on the periodic crystal, whether it is a long range order or a short range order, you will generally get sometime constructive interference and sometime destructive interference. From the constructive interference, you will get the information about the material what you are diffracting. Okay, so that is the overall theory behind the X-ray diffraction. Okay, so that's what we do. Why X-ray? I already told you, I can skip. So how X-ray tube is made, it's physics, we don't bother so much. So then I told you the sample has to be single crystal. So we are not dealing with the sample like those things, the polycrystalline material. So we are discussing single crystals. So what is single crystal? So some of the examples I give for single crystals, which are naturally occurring or which you deal with day-to-day life. One is salt is a single crystal, sugar is a single crystal, ice cube is a single crystal, okay? Diamond is a single crystal, ruby is a single crystal. What do you observe? If you see them, what do you observe? They are very shiny, they have a definite shape. It can be needle, it can be rod, it can be block, it can be plate, it can be whatever, but it has shape, right? And it has definite edges. So that is the property. By looking at the single crystal you can see. Okay, so but in theory they have a long range order till infinity. Okay, they have a repetitive atomic units. Okay, so that is the single crystal. In polycrystalline, this repetitiveness will not last till infinity. It will have a short range order. So that is what it is called polycrystalline. So if it is a polycrystalline material, they are also crystals, crystalline, but they don't follow the long range order. They will last only for short ranges. Okay, so that is why you need to depend on, if it is a polycrystalline material, you need to do it on a regular XRD. So you will get only phases and quantification. But if you have a single crystal, so then you can put it on this instrument and then you can really do the structure solution. So then obvious question, particularly for this institute, because you do not have an X-ray diffractometer, right? You do not have a Porter XRD. So then you can ask me as well that yours is also single X-ray diffractometer. Why can't you do the Porter material? Why not put this only single crystal? Okay, so here this machine is dedicated for single crystal analysis. Okay, but it doesn't mean it will stop you there. You can do some Porter sample as well. Okay, but you cannot make real comparison by the result obtained by real XRD to the single crystal XRD. You can do up till phase analysis. Like this is my phase, you can tell. but you cannot tell the quantification. Simply because otherwise Bruker would not have made two diffractometers, right? They would have sold only one instrument. There are some physics behind it. Okay? So in case of single crystal, the X-ray beam is focused on the sample. Okay? Whereas in case of regular XRD, X-ray is focused on the detector. So that means the resolution what you get on an XRD for a powder sample or a polycrystalline sample is way better than what you get in single crystal XRD. So that is the only reason that you cannot do the quantification. Otherwise, you can do for phase analysis. You can easily do any of your powder. If you are just want to understand the phases of that material, just put it on this single crystal. It will take few minutes. Okay, so you can use this diffractometer as well as for the X-ray as a powder analysis as well. But the main purpose of this instrument is to attain the single, the structures like this, which can be obtained by having the single crystal. So that is why we say, some people call SC-XRD, single crystal X-ray diffractometer, SCD, single crystal diffractometer. Both are same, mainly used for the three-dimensional atomic structure determination. Where it is used? Essentially in R&D, research and development. Okay? Because you are preparing new compounds. So any publication without your structure is kind of incomplete. If you have a structure, that's a final proof, right? So with this machine, your research or the number of publication will exponentially increase. Okay? Because you have prepared a compound, you test with NMR, and then if you can happen to grow a single crystal, few minutes to few hours to days, you will be able to get the structure, and then you can understand your properties better. Okay? So essentially used for R&D, sample should be single crystal and little bit of crystallographic knowledge is required. Nowadays with the software, 90% of the thing will be taken care by the software. Okay? You don't really have to learn what is crystallography and so on, because it's not time now to all those things. But some knowledge about at least what are the crystal system, what are the, how I can solve my structure. So little bit simple understanding of crystallography will help you to solve your structure in very fast time. Okay, so just to encourage you, this is, you can see the number of structure published over the years. So there is an exponential growth thanks to all chemists and other researchers who prepares a new sample, and thanks to all the diffractometers, which makes the life easier to get the structure. You can see there is an exponential growth every day, every year, every month. You can see there is a lot of structures are getting published. Okay, so when you get your structure, you can always report that in the CCDC. You can make the publication later, but you should report your structure that I have found out the structure of this already, and then you can deposit already in the CCDC. So that is what here I'm taking the information from. Okay, so then that is your structure. Nobody else can claim it. So then once you write a paper, you give a reference to that I have already deposited with this CCDC number. So that is what the overall procedure of that. So again, I might be repeating. So if you are an organic chemist, if you are an inorganic chemist, if you are a metal organic chemist, if you are a coordination chemist, if you are a natural product researcher, if you are a bio or a protein, everyone can use this single crystal diffractometer to arrive at the structure. So there is no limitation of number of atoms, but provided you have to have a single crystal. Okay, now sample has to be single crystal. So we will say that practically no scientific publication of a new compound without its crystal structure. So generally, if you say that, if you want to say that, I have prepared a new sample, so without its structure it is incomplete. Okay, if you have the structure, so then that's an ultimate proof. So this I can skip because this is kind of a marketing slide, so I can skip. Okay, so then what is structure good for? What you can get from the structure? So you will understand what is this compound is made up of. okay? And then you can also understand how they are connected, whether they are connected by covalent bonds, whether they are connected with hydrogen bond, whether they are connected with ionic bonds, whether they are having some intermolecular interaction, why my molecule is become pharmaceutically active, why my compound is having interaction with particular material, why it is becoming hard, why it is becoming soft. So you can understand those stuff. So you can understand not only the bonding situation, you can also understand the packing, how they are interacting with the solvents, intermolecular interaction, hydrogen bonds. You can study exactly about the bond lengths, whether it is a single bond or a double bond or a metallic bond, ionic bond, and everything. And then you can also study about whether this compound is pure or whether there is some stoichiometric changes, whether there is a substitutional with some other metals and so on. So you can study about those stuffs. And then you can study about, in detail electron density, how the electron density distribution happen between these atoms as well. Okay? In general, you can understand all the properties. If you have a structure, you can understand the properties much better. If you don't have the structure, it is not easy to understand the properties of the material, why it is behaving so. Okay, so that is the sole purpose of this diffractometer, to get the structure, and by understanding the structure or by obtaining the structure, you can get all the information about the properties of material. Especially for your cases here. So for you, this absolute configuration is very important. You want to determine the stereochemistry of your molecule, right? Single crystal method is the method to determine your stereochemistry. So for that, because you are dealing with lot of organic molecules, for you it is very important to understand whether it is R, S, okay, cis, trans, whatever. So all these then you can determine by using the single crystal diffractometer. Okay, it will tell you about the properties, but then you need to see that how the molecule are packing based on how they are oriented. Based on that, you can say whether it is a right-handed R or S, whatever. Okay, so that's the idea about this instrument. So then, how does the instrument or the overall procedure of single crystal XRD? Okay, so this is the workflow of a single crystal diffractometer. So you prepare your sample in your lab. Okay, so then obvious question is how you can prepare, right? So there are several methods. I can see already a lot of crystal in your institute already. So sometime you just take it to the NMR, and then you already see while coming back that on the sides of NMR tube you have a single crystal. So best way, or the majority people use, is the slow evaporation method. So what they do, they take a sample and they dissolve or supersaturate with the solvents, which it gets dissolved in, and then let it cool or let it evaporate, and then there is a high chance of getting single crystals. Okay, so you need to use sometime mixture of solvents, you need to use different solvents, you need to use sometime water and other stuff. So slow evaporation is one of the method and the most used method. And different ambient conditions, like you can put it in fridge, you can put it in the glow box, you can put it outside, you can put in different. You might see that different time of the year you will have a different crystallinity. Okay, so everything matters. And then there is also some sublimation method, there is also some sitting drop method, there is some hanging drop method. So there are plenty of methods to obtain single crystals. So protein people generally use some robots to put crystallization, because it's not easy to get protein crystals. So they put several thousands of trials with different molar concentrations to get some crystals. Okay, so that's what, because if you have a crystal, so then you can arrive at the structure in no time. Okay, so you get something single crystal like this. Ideally, we would like to have a crystal with the solvent in it. Okay, it's fresh. If it's get dried, sometime when you are submitting the crystal to the crystallographer or the operator, what it looks like, okay, it looks like a beautiful crystal, but he will not be able to measure on the same day. He will have to wait for the sample queue. So maybe he measure after 2 days or 3 days. And when he sees that, the crystallinity is already gone. Then you will get disappointed that, oh, what happened? The crystal was good, now it is not. So ideally, you should submit a crystal with the solvent which you have, grown your crystal. So there is a more chance that crystal can grow even better, or it can stay, the crystallinity will remain intact. Okay, so that is why I always prefer to have a crystal with the solvent in it. Okay, so once you get that sample, the sample preparation is the crucial part. No experiment technique will, without the sample preparation, will work. And the sample preparation is the absolute crucial part. And single crystal is also the same. If you put some rubbish crystal, the data will be rubbish. If you put some good crystal, the data will be good. So no instrument can make a magic and then give you some solution. Okay, whatever your input is, the output will be as it is. Okay, keep this in mind. If your crystal is not good, it will not be good. You cannot make it good. So if there is some challenges, like if you have a twins and if you have some disorders, so there is always a software to handle or tackle them as well. But if your crystal is bad, it is bad. You cannot make it good. Okay, so what in that case you have to do is you need to try different solvents and different environments to get the better crystal. Okay, so then once you get a better crystal, so you need to bring it under the microscope, because we are mounting a crystal is few micron size. So you can measure a crystal from 500 micron to 5 micron. Okay, you can really go up to 5 micron if you can able to see and mount. Okay, but organic crystals, generally you would like to have a crystal which is bigger. Okay, why? Because organic crystals will have carbon, hydrogen, nitrogen, oxygen. They are not having lot of electrons. They have 8 electrons, 7 electrons, 6 electrons. But if somebody is working on an inorganic chemistry, he is using some ruthenium complex or a gold complex or a copper complex. He has the electrons of 30 electrons, 50 electrons. They are scattering very nicely. So smaller crystal will work. But if you have a organic crystal, it is always better to have a bigger crystal. It doesn't mean that you cannot do smaller crystal. It requires more time, because you need lot of X-rays to expose. But if you have a bigger crystal, so then your data quality will be better and your time can be taken to collect the data will be much lesser. Okay, so
now my question is, how do we decide whether it's a good crystal or it's a bad crystal?
yeah, I'll come to that.
Okay.
Okay, so I have few slides for that. How we can classify that is a good or bad. Okay, so I will come to that. So then that's the sample preparation. That you need to see the crystal under the microscope and then you need to pick it up. I have few slides of how we actually do in the lab. Okay, so then you put it with the loop which is made up of nylon, because it is X-ray transparent. It does not give you diffraction from the nylon. So that's why we take that nylon loop, you scoop the crystal and put it onto the diffractometer. So basically you will shine the X-ray for every side of your crystal. Okay, so it depends on the scattering power of your crystal. It might be taking 1 hour data collection, it might take a 10-hour data collection, it might take 20 hours data collection. It depends on the scattering power of your crystal. Okay, so nowadays with a much better source, much better detectors, the data collection has become very, very small. But whereas in the earlier days, you need to take lot of time. Okay, so then you collect the data and then the software will take care about processing this data and it will give you an electron density. So based on the electron density, you will be able to say, the software already says that, okay, this can be your molecular structure. But then you need to evaluate, okay, does my chemistry make sense? Okay, does this carbon is in the carbon place, nitrogen is in the nitrogen place, oxygen is in the oxygen place. You need to make an evaluation and finalize the structure. So your involvement is mostly on the sample preparation and then refinement. Rest are all is almost just in the buttons. Okay, so that's what this slide says. So your involvement is required in the evaluation or the refinement of your data, and at the sample preparation. So sample preparation is the crucial part of your single crystal diffraction. And this is the instrument what you have got here in IHBT and one of the top end machine, okay, with two X-ray sources, two independent X-ray sources, okay. Why not only one? Why we have two X-ray sources? You have both molybdenum and the copper. I'll come to that, okay. So if you look at the inner beam of this diffractometer, you can see we don't do anything here. Our working stage is only the transparent, you can see there. So that's the working area. And if you look at, and this is the schematic diagram of a diffractometer, where you have two X-ray sources, copper and a moly, and you have a 4-circle kappa goniometer, and then you have a big area detector. Okay, and you can measure your crystal at room temperature, low temperature, and high temperature. Low temperature up to 100 Kelvin, high temperature up to 400 Kelvin. So generally, you would either like to measure at room temperature or low temperature. If you want to determine an absolute configuration, which is very important for you people to understand the stereochemistry, you must collect in low temperature and your crystal has to be good. So don't just give some average quality crystal, because you are trying to determine a very accurate part of your structure. So for that, the data has to be really good. So the data has to be really good means your crystal has to be really good. Okay, so just don't then complain to the operator, okay, I have not able to get the absolute configuration. If you want to get an absolute configuration, your crystal needs to be good and you need to collect at low temperature and you need to measure with copper source. So that is the purpose that you have a dual source. Okay, you are using a copper radiation because you want to determine a stereochemistry of your molecule. That's the absolute configuration, which can be determined only by copper. Okay, or most of the people believe that it is only determined by the copper. Okay, because it gives a better anomalous signal. I will not put too much physics into this talk. Okay, so for you to determine an absolute configuration, so you need to use a copper X-ray source. Okay, and you need to collect at low temperature and your crystal has to be good. Keep this in mind. Okay, if you put just an average quality crystal, you will get the structure, no problem. You will get the three-dimensional structure, but you will not be able to get the the stereochemistry of your molecule. So what is the parameter which signifies the stereochemistry of the molecule is, in crystallography we call FLAC parameter. F-L-A-C-K. FLAC is the scientist name. The FLAC parameter has to be 0. That means you have correctly determined your absolute structure determination. Okay? FLAC parameter has to be 0. So if it is 1, so then you need to invert and then refine it. If it is an 0.5, it's an inertial one. Okay? So you could not determine, it's a 50-50. So to get the value 0, so that means it cannot be like 0 just, it will be in the second decimal place, 0.0 something. To get that value accuracy, so you need to have a very good quality crystal. Okay, and you need to collect at low temperature and you need to collect at copper source. So that is the purpose of having copper. And another significance of copper is you want to do some protein crystallography. For you, the X-rays have a different properties. Okay, I think I have a slide. Yeah, here. Okay, here is a slide for that. So you can see generally in single crystal we use 3 wavelengths: copper, molybdenum, and silver. We don't use silver quite often. We use mainly copper and molybdenum. So molybdenum is having the wavelength which is half of the copper. If you look at the intensity, right, copper is highest. Wavelength, copper is highest. Energy, copper is lowest. Okay? So you have an idea in the future also, or now also, you want to do absolute configuration. For that, Copper is mandatory because you get the better anomalous signal and you have a better intensity. Okay, that is the purpose of having copper radiation. And because of its less energy, it is also suitable for all proteins and peptide applications. Okay, copper radiation is preferred whenever your crystal is weakly diffracting, so you need more intensity. Copper is an ideal solution, and then it gives a better anomalous signal, so you can determine the absolute configuration of a pure organic molecule. If you want to do some protein, if you want to do some peptide, it is better to use with copper because it has a less energy as well, high intensity. Less energy will not damage your crystal, high intensity will give you better information about your crystal. Okay, that is the purpose of having copper. Then why not why molybdenum? Okay, so molybdenum is actually most suited for all other applications. Like if you want to determine like you have a sulfur, you have a fluorine, you have something like that. So then for structure determination, molybdenum is the ideal solution because it has a shorter wavelength and then it will collect the data in a much faster way. Okay, and then most of the structure till now published, if you look at that, it's using the molybdenum. It has a less absorption as well. Okay, so that is why it is preferred radiation for all small molecular applications. But whenever you deal with a very pure organic molecule, like in this institute, so copper is preferred because of the intensities, because of the determination of the stereochemistry, and because of the intention of doing proteins and
One quick question. Now, you told that if actually you're doing this X-ray diffraction at low temperatures, it's preferred. I mean, let's say if I talk about proteins,